There we go. Let's go ahead and start. Let's just do the announcements verbally. So there's a homework due tonight, online homework. So check that out. It's on Pearson. Then there's a homework due next Monday, 11:59 p.m. And the second exam is not this Thursday, but it's the next Thursday, October 31st. It's on Halloween. All right, so I'll get the like a practice exam like I did last time, and a review page so you know what topics to review like I did last time. I'll get those up sometime this week, and then next week I'll set up a review session in the evening, just like last time, so you can come to that, and I'll record all of that so you could watch that. So the exam, I decided to add another chapter on to this exam too. So it'll be through we should be able to get through chapter 13 by the time we get there, just so that what we're talking about in class matches up to what we're doing on the exam. So you don't have like a full week where we're covering stuff that you're not going to be tested on. But yeah, I'll put that on the review sheet so you know exactly what you need to know for the second exam. Yeah, and I think that's all the announcements. So, all right, so let's look at we're talking about probability here. So let's look at this example. If there's no questions on the exam and all of that, any questions? If you dress up, it's okay to dress up. It's Halloween, so if you feel the need to dress up, you can definitely dress up. All right. So let's say we flip a coin 10 times and we get heads 10 times. So the question is, well, that is unlikely, but it is possible. And then would that mean that we're going to get tails? Like we have to get more tails now because of that? Well, not necessarily. We could keep flipping heads. So we wouldn't want to use the false law, the law of averages. That's what this question is right here. So we're not due to get tails. But the law of large numbers does say that in the long run, we will approach 0.5. So maybe 1,000, 10,000, million flips of the coin. All right, so let's look at the here. So now we get 5 heads, 5 tails. So we flip the coin 10 more times, and we want to find the cumulative proportion of heads after 20 trials. So we've got the number of heads over the number of flips. So in our first 10, we had 10 heads. And then in our second 10 trials, we had 5 heads. And then we've done 10 plus 10 flips total. So that gives us 15 out of 20. Which is 0.75. All right, so next time we do 15 heads and 15 tails and 30 more flips. So we have number of heads over number of flips. And so now we have 15. We have 15 more heads. And then we had 20. And then we have 30 more flips. So we're just keeping track of how many heads out of the total number of flips here. And this is 30 over 50, which is 0.60. All right, so we're getting a little closer to our 0.5 that we expect that we're going to, using the law of large numbers, that we will approach that 0.5. All right, so now we've got 475 heads and 475 tails. So we had 30, and now we added another 475. And we had 50 flips, and we added 950. So that's 505 over 1,000, which is equal to 0.505. Right. So as you can see, we're even closer to that 50% there. So law of large numbers in action here. So this is just again saying that the law of averages, it's not true. You can't know in the short run what each individual flip will do. But in the long run, you can know that you will get around, you'll get pretty close to 50% heads, 50% tails. Okay, so types of probability. So there's 3 types here. We've got a probability that's from data. This is from data. It's an empirical probability. Oh, sorry. There you go. All right. So from data, empirical, that's what that means. And for example, you could roll some die. You could see what the probability that the total will be 14 or greater. So you'd roll the 3 die. You could roll them 1,000 times. And you could count up how many times you get 14 or greater if you count all the pips on all those die. And that way you wouldn't have to do any theoretical math. You could just count it up. But yeah, it would be a lot of work to actually do that, like 1,000 times. It'd take a long time. All right, theoretical probability. So that's based on a model. So if you're assuming that a die is a fair die and that all the outcomes are equal, you can say that you would have a 1/6 probability of getting any one of those sides. And then you can use this to calculate what the probability should be in the long run. And then you could do personal or subjective probability. So this is just based off like, it's kind of like a guess or what you feel. Maybe like a meteorologist gives a 25% probability of rain tomorrow, or 0.25. So they've got some kind of a belief there. Or maybe an economist says there's a 0.50 probability that we'll enter a recession this year. Some kind of belief. It's somewhat, it's subjective. So it's not from data, and it's not, that's a hard thing to get a theoretical probability from, because you don't actually know the probability of all the outcomes. Okay, so however we assign probabilities to outcomes, they must make sense. What does that mean? Well, for starters, should be between 0 and 1. If you say the probability is 5,000, that does not make sense. All right. All right, so let's learn some new words here. Probably just review, actually. We got some what is a sample space? So that's a set of all possible outcomes. And usually we give it, we say it's a capital S right there. All right, so let's say that we were going to toss a coin and record the outcome. And we want to write the sample space. So the possible outcomes, so this is set notation, that's a set bracket. We could have heads or tails. All right, let's say you randomly select a student from Stat 216 and record their class. So we could have freshman, sophomore, junior, maybe with an R, senior, graduate, or other. So other would, you know, maybe you're just like oh, maybe you're like after a senior or something like that, or you're just already have your degree and you're just taking some classes. All right, so event that randomly selected student is a sophomore or a junior. All right, so here we've got, you could be sophomore or junior, all right? And you just list them out, so like that. Event the student is not a freshman, that'd be all the ones that are not freshmen. So you list out everything else, like a sophomore, junior, senior, graduate, other. All right, then the student is a sophomore. We'll call this capital C. So we can just have one object in their set, one entry there. And then D is already written out. It's a freshman or a senior. All right, so this empty set, it's this symbol right there. It's the empty set. It's used to denote a null event, so saying that something couldn't happen. All right. Damn. All right, so let's learn what a complement is. So that's just everything else besides the event. So you'd write it as a complement. There's a C in the as a superscript. And it's the set of all outcomes in S that are not in A. So let's go back to what A was. It was the sophomores and juniors. So the A complement would be the freshman, senior, graduate, other. Graduate, other. All right. Okay, disjoint events are events that have no outcomes in common. So say like are A and B above disjoint, so A, sophomore and junior. But B also has sophomores and juniors, so they are not disjoint. And this is no. Are A and D disjoint? So here, sophomore, junior, freshman, senior, yeah, they have no elements in common. So this is a yes. right there. All right. So disjoint, you could think of them as saying that those sets are non-overlapping. All right, so 181, page 181, we got independent events. So that's if one event does not affect the probability of the second event. It's independent. 2 bullets here. This just says that you can multiply these probabilities together if they're independent. That's the multiplication rule right there. Multiplication. All right. So usually we want events that are independent so that we can use this rule and yeah, find what the probability is that A happens and B happens. So a lot of times we assume independence, but you want to think about it a little bit just to see if it actually makes sense. All right, let's look at some examples here. So let's say we have flipping a coin or rolling a die. Let's say we do this 3 times. We flip a coin 3 times. So we would multiply them together 3 times. 1/2 times 1/2 times 1/2, and you would get 1/8 right there. All right, so flipping a coin is, the first flip doesn't affect the second flip, so it shouldn't be a problem there. All right, babies, having babies. So if you have a boy, that shouldn't affect whether you have a boy or a girl the next time. Yeah, we assume that they're independent. So if we wanted to know what's the probability that the first 2 children born to a family are both girls, then you just multiply those probabilities together. So we've got yes. So I think it's actually, yeah, I'd have to look that up. I always thought that was a little more likely to be born a girl than a boy. But here, let's just assume that boys have a probability of 0.51 and girls have a probability of 0.49. So yeah, pretty close. It's not quite a coin flip, but really, really close. So yeah, you'd multiply that by itself, and you get about 0.2401 that you have 2 girls. And again, we're assuming that there's an independence here between each birth. All right, so here's a kind of a tricky question for you. I actually thought about this a fair bit, I'm not a biologist or anything, but in population models, in biology, we may assume that the survival of individual animals from one year to the next are independent events. Is this a reasonable assumption? So does one animal affect the survival of another animal? Yeah, but okay. What about if I phrase the question this way? Does the death of one animal affect the death of another animal? Well, okay. So like if I drop down dead right now, would that mean that someone else is likely to drop down dead? Maybe. Huh. Oh, yeah. There you go. So there is that case. So yeah, this is a complicated question, and the way I answered it was saying that predation occurs on an individual basis. But if you had like a starvation situation, or if the parent was the one that got offed, then you would have it would not be independent then. But let's just say that everybody's grown up, which animals grow up pretty fast for the most part, so it's probably not super likely that would happen. And yeah, it would depend on the species, of course, because some species like snow leopards, they're like extremely solitary. So snow leopards are definitely independent from each other. And bears are very independent of each other. But then other things like, lemmings, maybe lemmings aren't so independent of each other. All right, so I just said yes, and then there's exceptions. So predation events, or predation occurs on an individual basis. An example of an exception would be a plague. So if an animal gets sick, then it could be contagious, and a lot of other animals get sick, and then a lot of animals die because of that one animal's issue. Question? Yeah. So you do make this assumption. Do you make this independence assumption? No? That's not involved with the model? Right. Right. Okay, so you just think that this is just flat wrong. We don't assume this. Oh, predation? Let's say you, like a predator, they kill you, they eat you. Like in maybe the Aliens versus Predators. It's like that. So yeah, if this hurts you as a biologist, you could just throw it out. That's fine. We just wanted to think about this. If we need to assume that, then you could. So. But if you don't like it, just throw it out. All right. All right, here's a note for you guys. So disjoint and independent are not the same thing. Okay, let's try think about this a little bit. So independent was whether or not two events, whether one would cause the probability of the other to go up or down. And then disjoint was whether or not they could occur at the same time. So it's a very different ideas here. And pretty much with disjoint events, you can use addition rule and add them together. With independent events, you can use the multiplication rule and multiply them together. So it's the difference between a plus and a times in the math of this. So very different. All right, so here's a little bit of notation. So an event A in a sample space S, probability of an event A is denoted by Here's another P. So this one's a capital P. This means probability of A. So you'll know that this P doesn't mean proportion because we're talking about events and we're in the context of probability. So it's slightly different than talking about like a proportion P, like with that or parameter P or a statistic P hat. Also, it's capital, so slight difference there. All right, so here's the probabilities have to be between 0 and 1. That's always, 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 always true. You can't give 110%. You can't have a likelihood of 110% or 1.10 here. All right, so probability of the any event that some event in the sample space occurs is 1. All right. So this is the probability that some outcome occurs. So something has to happen, right? So the one of those things happens, that always happens. So that's a 1. Probability that the complement of A occurs is 1 minus probability of A. Right there. So this is called the complement rule. Capital P. It's 1. All right. So if you think about the space of everything that could occur, you've got A, and then you've got the complement of A. So if you've got, say, a 30% chance of something happening, you've got a 70% chance that it doesn't happen. That's all this is saying. 1 minus the probability of A. Right? So yeah, you'll use this one a fair bit. So definitely know that one. You could also note that probability of A plus probability of A complement is equal to 1. That's just another way of writing the same thing. Right there. Maybe you might want to use that instead sometimes. All right, so if we've got disjoint events, A and B, you can use the addition rule. And what that's saying is that if A or B, probability of A or B, okay, or you add them together. Probability of A plus probability of B. Right there. And then if you have independent events, you multiply. So probability of A times probability of B. And you would use this word and right there. Question? Oh yeah, sure. Let's think about the freshman sophomore thing. So let's say that well, you can't be both a freshman and a sophomore at the same time, right? All right, let's just say that you can't. And let's say you had a probability of being like, oh, I don't know, 20% that you're a freshman and 18% that you're a sophomore. So that would be a case where those two events are disjoint. You can't be both a freshman and a sophomore at the same time. And you would add those probabilities together. If you wanted to know what the probability is of being a freshman or a sophomore. Let me just write that out. Probability of being a freshman is equal to 0.20, we're assuming that. Probability of being a sophomore is equal to 0.18. So the probability of being a freshman or sophomore is 0.20 plus 0.18, or 0.38, which equals 0.38. Okay, so yeah, multiplication rule. Yeah, it's like with the coin flips. All right, so let's look at, we have some marbles. They're yellow, they're blue, they're green. So there's three yellow, 4 blue, 8 green ones. And we want to know, let's write down what the events are. So we've got Y. Event that a randomly selected marble is yellow. G would be that the marble is green. And if we wanted to, if we were curious about blue, we could, or we used blue marbles at all, you could say that that was maybe a B. So here we want to do, what is the probability that randomly selected marble is either yellow or green? All right, so let's find what probability of Y is individually, and let's find what the probability of green G, that's green, is individually. And we had a total of 15 marbles. So 3 yellow plus 4 blue plus 8 green. So 15 marbles. And then the yellow ones, again, there were 3 of them. And then with the green ones, there were 8 of them, I think. 8, yes, 8. All right, and then here we want the probability of Y or green. Or green. So these are disjoint. We've got that word or there. So we have to decide, should we add or should we multiply? And we want to add, because they're disjoint. We have the word or. So this is equal to probability of Y plus probability of G, or that's green. 3/15 plus 8/15 equals 11/15. All right. Any questions with that? You guys look like you have a pretty good handle on this. All right, so let's make it a little tougher. So what about, what if we want to select three marbles? And we're doing this with replacement, so we're putting them back in. So what's the probability that you select all green marbles? So there we've got, let's do subscripts like sub 1, sub 2, sub 3 for if it's the first, second, or third marble. And then we have all green marbles. So they don't say and or here, but we have to decide, do we use the word and or do we use the word or? So here, these are all have to be occurring. So you have to have the first marble be green and the second marble be green and the third marble be green. So we use that word and. So we've got probability of that the first marble's green, second marble's green, and the third marble is green. All right, so here each marble pool is independent. So if you pull a green marble the first time, you're just as likely to pull a green marble the second time. So now we have to decide, okay, are we doing the addition rule or the multiplication rule? And it's kind of a giveaway, so we have the word and there, so we're using the multiplication rule. So we've got, what was it, 8/15 times 8/15 times 8/15. And that is equal to Oh, I should have written another step here. Yeah, probability of green one times probability that the second one's green, G2, times probability that the third one's also green. Right there. And then that gives us 0.1517. All right, so there's not so many, you know, you're deciding, do you add them or do you multiply them? It's not so bad. These ones we multiplied. So what about no green marbles? Whenever I see the word no, I just want to use the complement rule. It's usually just easiest just to use the complement rule. So let's use the complement rule. So if okay, so if we have all green marbles, well, we could find what the probability that would not be a green marble. All right. So what's the probability that would not be a green marble? Yeah, 1 minus probability of a green marble. Or in other words, a yellow or a blue marble. It would be 7 out of 15. So there we used our complement rule. Seven fifteenths. All right, so now we want to, well, the first one has to be not green. The second marble has to not be green. The third marble has to not be green. So we would want to use the multiplication rule here. So first one's not green, and second one's not green, and third one's not green. So we'd have probability of the first one's not green times probability that the second one's not green times probability that the third one's not green. It's just 7/15 times 7/15 times 7/15, which is 0.1016. All right. So that kind of makes sense. All right, at least one green marble. Okay, so we could have one green marble, we could have two green marbles, or we could have three green marbles. But probably the easiest way to do this is to say we want to subtract that there's no green marble. So we take the complement of that. So if the opposite of saying that there's no green marbles is saying that there's one or two or three. So we would want to take 1 minus that there are no green marbles. See? And G2 complement and G3 complement. That would be 0.8984. All right, what about exactly two green marbles? All right, so let's try to imagine. We're trying to imagine pulling out marbles. So, or you could find some marbles and do this. I didn't bring any marbles. All right, so you could pull a green marble the first time, green marble the second time, and you've got exactly 2. So a keyword here is exactly. So you can't have 3, you can't have 1. So we would not want to pick a green marble the next time or the third time. Or you could pick a green marble in the second and the third marbles, or you could pick a green marble the first and the third. So those are the only ways that you could pick exactly 2 green marbles. And these are disjoint, so you can't simultaneously pick green marbles for the first and second, and also pick green marbles for the first and third only. All right. So what we have here, so we've got the probability that we've got the first one's green, the second one's green, and the third one is not green. We've got the probability of the first one's green, second one's not green, and the third one is green. So that gives us 1, 2 green marbles. And then we've got the probability that the first one is not green, second one is green, and the third one is green. So it should be the second one and third marble are green. And then these are all disjoint, so we can also use the addition rule. So we use the multiplication rule here to find each of those probabilities. And then we would add them together to find our total probability of all 3 of these events right there. All 3 of these outcomes. All right, so this, I'm just going to write the numbers just to save some space. So you've got 8/15 times 8/15 times 7/15. This one is 8/15 times 7/15 times 8/15. And then we've got 7/15 times 8/15 times 8/15. All of those will give us the same number of 0.1327. So that means that our probability of exactly 2 green marbles is equal to all of those summed together. 0.1327 plus 0.1327 plus 0.1327, which is 0.3981. All right, so now we know having 3 green marbles, having 2 green marbles, and having, I think we found, yeah, one green marble was our first one, I think. No, we haven't found that one yet. But let's make a table. So we've got number of green marbles. In 3 draws. And then we've got the probability. So let's say we had 0, 1, 2, 3. All right, so we had the 0, 1. No green marbles was 0.1016. 1. So we've got at least 1, but we don't have exactly 1. We actually didn't find that. But we have exactly 2 was 0.3981. And then 3 marbles was 0.1517. And now you could use the complement rule with the sample space. So the only options are no green marbles, 1 green marble, 2 or 3 green marbles. So you know that all of these add up to 1, or the probability of getting the sample space. So you could just subtract off these 3 from 1 to find how likely it is to get exactly 1 green marble. Or you could just calculate it again, like just work like another problem like this and figure that out. So you would have you do kind of like in number 5 here, but instead of 2 green marbles, you just have like the first one green, the second one green, the third one green, and you'd add them up like that. So it ends up being 0.3486. Right. All right, so I think we've just got a little bit on this last page here. All it says is that we're skipping the Bayes rule and conditional probability. So let's just end right there because that's great. And we could start with the new, the last, or chapter 13, that's the last chapter on the test 2 on Wednesday.